Hello everyone, welcome to Scaling Chemical Equations. It is the second video in the Scale Factor Stoichiometry series. The first video is titled Cookie Stoich, and if you haven't seen that yet, you'll need to go and watch that before you can make sense of this video. This video assumes that you have seen that earlier video and that you have seen how to create scale factors and have some idea of what that word means when I say scale factor. So if you haven't watched that video yet, please go do that. If you have, let's move on. So in order to understand this video, you also, in addition to the scale factor, need to have some idea of the mole as a unit of chemical measure. I'm not going to say a lot about that here, other than to say that a mole is a convenient number of atoms to work with. It doesn't really work very well for a chemist to simply have one molecule of nitrogen to react it with 3 molecules of hydrogen. That's just not a convenient thing to do. A mole has a convenient number of chemicals to work with, and so that's the amount that we're going to be using in our chemical reactions. For visualization purposes, a mole of water is about a quarter cup. I hope you've already seen how to represent chemical equations, represent reactions with chemical equations, and how to balance chemical equations and understand why chemical equations need to be balanced, what the purpose of that is. After this video, you should be able to create scale factors for balanced chemical equations, and then you should be able to apply those scale factors to rescale chemical equations. Let's go ahead and get to this. So chemical equations are a convenient way invented by clever chemists in order to put a lot of information in a small amount of space. These equations right here are shorter ways of writing all that information right there. And anytime you take something that has this much information and you compress it, sometimes you can lose sight of what's important and what all is being represented. What's important for us is to focus on what these numbers mean and what they represent in terms of the amount of chemicals being used. We are going to be putting the mole in instead of just leaving the numbers by themselves, and we will be using the ones, and we're not going to pay attention to phase. So the chemical equations are going to look like this. 1 mole of nitrogen plus 3 moles of hydrogen reacts to make 2 moles of ammonia. 1 mole of zinc plus 2 moles of silver nitrate reacts to make a mole of zinc nitrate and 2 moles of silver. And finally, 2 moles of sodium azide decompose to give you 2 moles of sodium and 3 moles of nitrogen gas. Let's go ahead and start rescaling these equations. So let's say you're running a fertilizer factory, and you need a lot of ammonia gas to make your fertilizer. You need 500 moles of this. We're running an industrial scale reaction here. How many moles of nitrogen are you going to need? Well, when we look at the chemical equation, we can see that 1 mole of nitrogen is what we normally use, and 2 moles of ammonia is what we end up making. So our standard amount is 2 moles. The situation amount is 500 moles. Situation reaction, 500 moles. Standard reaction, 2 moles. Please recall, scale factor is situation over standard. And so we have 500 moles of nitrogen divided by 2 moles of nitrogen, and that gives us 250. In the Cookie Stoich video, I didn't talk about units at all, but we are going to be paying attention to units now. And when we have moles of nitrogen on top and moles of nitrogen on bottom, they will cancel with each other, and we are left just with the number 250. That makes scale factors really convenient in chemistry because, as not having units, you can apply them to anything. And this will allow us to apply the 250 to the entire equation. So we're just going to apply 250 and distribute it through. And when we distribute that 250 through, we have this new chemical equation, 250 moles of nitrogen plus 750 moles of hydrogen makes 500 moles of ammonia. We can see there's the 500 moles of ammonia, which is what the situation called for. And the question itself asked us how many moles of nitrogen we required. And there it is, right at the start, 250 moles of nitrogen is what's needed. Let's go on to another example. A chemistry student reacts 0.05 moles of zinc with silver nitrate. How many moles of silver can they make out of this? Let's look at the standard chemical reaction. There it is. You can see that the standard amount of zinc to use is 1 mole, but in this case, the situation has given us 0.05 moles of zinc. So there's our situation value. The standard uses 1 mole of zinc. Scale factor is situation over standard. There we go, 0.05 moles of zinc will be divided by 1 mole of zinc. Like before, the moles of zinc on top will cancel with the moles of zinc on bottom, and we're left with a scale factor of 0.05. 0.05 doesn't have any units. We can apply it to the entire equation, and the rescaled equation looks like this. 0.05 moles of zinc plus 0.1 moles of silver nitrate will react to make 0.05 moles of zinc nitrate and 0.1 moles of silver. So there we can see at the start of the equation the 0.05 moles of zinc that the situation told us we had. And there at the end of the equation is the answer to our question: we can produce 0.1 moles of silver. Our final example, we're going to look at the sodium azide decomposition. This is used in car airbags to inflate them quickly. And a car airbag might need about 0.432 moles of nitrogen gas in order to protect the driver. How many moles of sodium azide are you going to need to use? And by the way, this is the actual reactions that's used, and I'd like you to note that it makes 2 moles of sodium. So I've always wondered if after an airbag goes off, could you find some metallic sodium in your airbag and then go toss that in water and watch it sparkle or maybe even boom a little bit? So back to the equation now. 2 moles of sodium azide will decompose to give 2 moles of sodium and 3 moles of nitrogen. Our situation says we need 0.432 moles of nitrogen gas, and I'd like you to try this on your own before I go any further. So please remember what you know about scale factors and situation and standard values. Pause this video, take a minute or two as needed to work it out on your own, and when you are ready to come back, I will be right here waiting for you. Okay, I hope you were able to come up with the following scale factor. You have 0.432 moles of nitrogen is the situation amount. If you look back at the chemical equation, 3 moles of nitrogen is the standard amount, and that's going to give us a scale factor of 0.144. That scale factor can be applied to the entire equation, and as we distribute it through, we can see that we will need 0.288 moles of sodium azide, and that will produce 0.288 moles of sodium and the 0.432 moles of nitrogen that the situation called for. Looking back at the original question, it tells us that, oh, that's right, we need to cancel our nitrogen on top and bottom, and 0.288 moles of sodium azide is what's going to be required. All right, so I'd like you guys to try it. Here are 3 fun chemical reactions. I've done all of these in my classroom. I take it back. I have not done the first one in my classroom. That one is actually very loud and explosive, and the last one's actually really quite smelly, so I've done it in the fume hood. But sometimes I'll just go ahead and do it outside. So I guess I wasn't telling the truth when I said I've done all these in my classroom. But I have done all of these, and they are fun to do. So please take a moment, pause this video, work through these equations, and see if you can come up with the answers. And again, I will wait patiently for you while you work through these examples. Okay, welcome back. I hope you're able to come up with the answers that I came up with, that this is the amount of carbon dioxide that you'll make, the amount of oxygen you make, and the amount of aluminum that you will consume. If you came up with all of those, then it looks like you are on your way to understanding the scale factor method and how to apply it to chemical reactions. In our next video, we'll be looking at how it applies to chemical reactions that have been measured using mass, and that is to say grams of atoms, grams of a chemical, rather than moles. Thank you, and I look forward to seeing you again in our next video.